Thanks to the other organizers who worked very hard. I'm really happy that Sayantan came before me because he gave you all the background material that I would have had to give you otherwise. So I'm going to tell you about some very recent work that we did on simultaneous measurements of dielectric and stress relaxations in, well, dense suspensions, which Sayantan just told you about, of microgel particles. So what are these microgel particles? These are basically particles that are constituted by chemically cross-linked polymer networks. They are of colloidal size, and they can actually change their shape as well as their size in response to certain cues. In this case, it's a change in temperature. Okay, so this is work done by my PhD student Chandeshwar. He just submitted his thesis. And by Paramesh. He used to be a postdoc. He's now a faculty member at SSIHL in Anandpur. And this paper just came out in print last week. Kabir told you about amorphous materials. We make amorphous materials in our laboratory. How do we do that? As you know, crystals, you have lots of balls and, you stack them up like cannonballs, you get a crystal. However, if the packing is disordered, okay, you end up with what is called a glass. So a glass being something that is structurally structurally like a liquid, but mechanically it's like a solid. And the dynamics are characterized by, the dynamics are slow and they sometimes show aging because these are metastable materials. Okay, how do we make our amorphous materials? So we make most of our particles, the colloidal particles that we make, we now have learned to make them in our laboratory. So we make something called P-NIPAM, poly N-isoacrylamide. That's the name of the particle. So we start off with a monomer. We cross-link it, okay? So you end up with these globules these colloidal globules that are about 300 microns in size. The chemical reaction that we use is called precipitation polymerization reaction. Anyway, so, there are certain protocols that we have to follow. And then we end up with particles that look like this, that are submicron sized, right? So colloidal sizes. So under a scanning electron microscope, this is what the particles looks like. So they are they are a little polydispersed in size. They're all spherical particles. Okay, and we take these particles and we make glasses. How do we do that? It's very simple. So these are thermoreversible particles, which means that when you decrease the temperature, they suddenly swell up, or actually how suddenly they swell, we know how to also control that. However, so what we do is we take a predetermined amount of sample at very high temperatures where the particles are collapsed, and then we decrease the temperature and they suddenly swell up and they pack close together. Okay, they get very randomly close packed, and very also they are like highly very close to each other in a very disordered configuration, and they form this glassy material. Okay, and it's been wonderful being able to synthesize our own particles, because we make these microgel particles and we make them as we want it. For instance, we can actually change the rate of swelling and deswelling. In another work, we had also shown how you can actually control the size polydispersity of these systems. So we can make controlled Gaussian distributions of sizes. So anyway, so this is our, I'll just tell you a little bit about characterization, because these are particles we made in the lab. So these are acrylamide, remember? So at very low temperatures, where the entropy of the water molecules is low, the water molecules, they form hydrogen bonds with the amide groups. The particles, they absorb a lot of water, swell. Okay, but then at higher temperatures, okay, where the water molecules are running around much faster, the molecules, they cannot form these hydrogen bonds anymore with the amide groups, and the particle, it ends up just expelling water and shrinking. Now this has been done to death, but I'll just show you how we characterized our particles. So we used a spectroscopic technique that Amarnath spoke about in the morning. It's called photon correlation spectroscopy. You can measure sizes, and you can see that as you change the temperature, as you increase the temperature of a very dilute suspension of these particles that we've just made, you can see that at the lowest temperatures, this is the hydrodynamic radius, diameter actually, so this is rather high, but then around a temperature of 32 degrees, it suddenly collapses, right? So it kind of shrinks to about, well, half its size. And how fast it shrinks, we can control that. So anyway, so what I need you to remember is that these particles are maximally swollen at around 20 degrees centigrade, and at 40 they are totally collapsed. And you can see these pictures here. So this is our P-NIPAN suspensions. These are dense P-NIPAN suspensions. It's transparent here because the particles have swollen, they have swollen up because they've incorporated water, right? So there's no refractive index mismatch, no scattering, therefore it looks totally transparent. But here, at high temperatures where it's totally collapsed, so these are like, tight globules of polymers, okay, no water, so there's a refractive index mismatch, so you can see how opaque it gets here. Now this is the experiment we've set up. This is a rheometer, which Sayantan also told you about. So these are the rheometer plates. So the bottom plate is fixed, and the top plate, it can apply oscillation. So in Sayantan's case, he was applying these step strains. We give these very large amplitude oscillatory strains, okay? And in between these two plates, so this one can rotate and oscillate, in this case oscillate, this one is fixed, this black thing here is the sample. So, okay, but in this case, our plates, these are also like capacitor electrodes, okay? So we connect this sample, okay, to a precision impedance analyzer, because we want to measure the dielectric properties, right? So then we use a 4-probe technique. We give these rather high voltages, so these create rather large electric fields, and we measure the current, okay, and therefore the complex impedance. Then from our data, because the current is of course not in phase with the applied voltage, right? Because this is a material that dissipates as well as stores energy. So then we can calculate the capacitance as well as a loss factor. And from the capacitance and the loss factors, we can calculate the complex dielectric permittivity, and then we kind of, we partition it into the real and the imaginary components. So here's some example data. So this is for just one sample. So this is the real part of the complex permittivity versus frequency. So we've applied frequencies over a huge range, 20 hertz to 5 megahertz, and we see that, so the real part, you'll see this has 2 relaxations, and we see these 2 relaxations no matter which temperature you're looking at, okay, and only of course for these densely packed suspensions. So, and here in the inset you see the, yeah, I'll finish really fast. You see the, the imaginary part. So the slow part comes from the segmental motion of the polymer, and the fast part comes from fluctuation of counter ions. So there's a lot of sodiums and potassiums that we've given when we made our samples, and then we fit data such as this to a relaxation model. Okay, and we see that as we increase the strain, we can see that the permittivities are decreasing. Okay, what we focus on is when the particles are completely closely, they're very, very closely packed, very, very densely packed. And when we calculate time scales of these, of the time scales of the dynamics, we see that the dynamics, actually the dipolar dynamics actually slows down. Okay, so this is something that we hadn't really expected. So we do see, for the maximally close packed particles, dynamical slowdown at the length scale of the dipoles. However, remember, we are also doing simultaneous rheology experiments. So at those same oscillatory strains, we see that the bulk stress response, it actually speeds up. Okay, so this we know by fitting our, so this is stress response data of the very closely packed samples, when the particles are maximally swollen. We fit it to a model that, we often use for glassy melts, and we see that the dynamic speeds up in the bulk. So basically the reason why this is happening is because when we are applying electric fields, there is local entanglement of polymer chains, okay, as a result of which you see the slowdown in the dipolar dynamics. However, you can think of these particles as forming clusters, and these clusters, they are ripped apart by the very large strains that we are using. So So basically using a single technique, we could actually measure length and time scales spanning about, 9 decades. So, and of course, I mean, this is what we called length scale dependent rheology.
This epsilon double prime somewhere you had, which was non-Newtonic. Is there resonance or something?
So that was
slide number 5.
So that is the yeah. I mean, yes, and but if you look at the frequency, okay, the time scale that you get out of it, that's actually I mean, it's the same the fast relaxation that we get. So
this peak is happening at some resonance frequency, is it? In set.
that is just the dipolar. That's the dissipation peak. Yeah.
So there's a natural frequency.
There is, yeah. It is basically you can link it to the very fast dynamics of the system. Sure.
So these particles are like spherical particles, more or less,
Yes,
right?
yes.
And what about the surface? Are they rough or smooth?
No, these are okay. So we can also make hairy particles. So you can take these particles and you can also cover them with shells of different monomers. So we do that if you want to change the steric interactions. But these are spherical particles, but only in dilute suspension. But then these are also compressible particles. They are deformable particles. So the data that I showed you when the particles were very closely packed, they're actually deformed. They're not spherical anymore.
So do you expect these two-step relaxation timescales, etc., they may change if the surface is rough, like you have hairy particles?
I mean, we have done it for rough particles, and yes, you do see, but there are other kind, because you also have these shell monomers. So but yeah, you do see these
Two-step
because
relaxation.
you'll always have some segmental relaxation, which is where the slower dynamics is coming from, and the fast dynamics is coming from counter ion fluctuations. So like I said, there are these sulfate ions on the surfaces. There's sodium and potassium ions, and so those things, if they are there for rough particles, you'll also see that.
Okay.
So once you prepare the system and go build this low temperature, and the particles swell up, and then it starts showing these dense dynamics. Do you see any other temperature dependence to that system, or
I didn't show you any temperature dependence, okay? And so basically, I just showed you when the particles are swollen, but then we also have a lot of experiments, where the collapse in the particle size is happening. And also, at higher temperatures where actually the particles become very hydrophobic and they can actually form a system spanning gel, okay? But in all the cases, you do see these same relaxations, because you always I mean the speed of the, for instance, the slow relaxation comes from segmental motion. The time scales change, but the relaxation is always there. So in most cases we can pick up that relaxation. Yeah, but what we don't see at other temperatures is the change in the rheology and the dielectric constants that we see when we apply different strains. So that only happens at the lower temperatures where the particles are fully swollen.
So